Martijn will continue with nonlinear polarization. Thank you.
All right, so I put the microphone on, just in case. Anyway, so what we were talking about before the break was this fact that this medium responds at a frequency when you don't drive it. And that makes it nonlinear. Now, that is only half the problem. And the reason is that it is perhaps all very nice and noble that this material oscillates at, say, double the frequency where it was driven, but somehow, what is the effect of that when you do a measurement outside your sample? And we will see that in general, the fact that it oscillates at twice its frequency doesn't do very much if you look at it from the outside. You have to do some, you have to play your cards very, very carefully, and in this second hour I will tell you what you need to do and what is involved. But the idea is somehow the following. Let me get my pointer. The rough idea is the following. You have not just one atom, of course, that oscillates at this new frequency. You have a ton of them. Okay? About 10 to the 26 or so per cubic meter. And so, since you have so many of them, you have basically each of these atoms acts as a little antenna. Okay? And what you want, of course, is for you to measure something outside, you need somehow the phase of those of the radiation coming from each of those little antennas. You want them to be in phase with each other. Or lacking that, you don't want them to be interfering destructively, because then you don't see anything. Now it turns out that in general, you will, unless you take precautions, these dipoles will oscillate such that they interfere destructively, and so you need strategies to deal with it. And we'll get to that in a minute. Now, let me just remind you of a little bit of E&M. And I won't dwell on this because this is all standard stuff. You start from the Maxwell equations, you do the standard tricks, and you find the wave equation where P comes in on the, sorry, what you do in nonlinear optics often is you write the polarization as on the right hand side as a separate term. Now, if you have just linear effects, this then is absorbed in this term here, and you get your n squares. The question, of course, is what happens when you are dealing with a nonlinear medium? Well, when you're dealing with a nonlinear medium, you do the same thing. You have a linear polarization and a nonlinear polarization, which depends on these quadratic and cubic terms. And now here you get this source term. You get your standard linear wave equation, and you get this source term, this nonlinear, this term that oscillates at a different frequency of where you drive it. And ultimately, this problem of what do you see from the outside when I put a light beam through a nonlinear medium comes down to solving this nonlinear wave equation. And we will find a number of ways of doing that. Don't worry about the stuff here down the bottom. This is what I mentioned earlier in the little demo I had. The simplest effect is second harmonic generation. So what I'll do now is just give you some ideas of the type of effect you're expected to see when you deal with these chi2 or quadratically nonlinear media. One of them is second harmonic generation. This is a very large one. This is used in an an astronomical observatory. This is to generate a guide star to do adaptive optics. So you have 532 coming out of the top here. It emits sodium atoms that are high up in the atmosphere. Sodium atoms form a small star-like object, a small spot. You aim your telescope at that, and then you know you have, from the fact that you know this is a small spot 50 kilometers up, you can work out what the atmosphere does to the light when it comes down. And then you drive your mirror to undo that. And that is a way of getting good quality, high quality astronomical images. All right, let's look at another nonlinear effect, and again a quadratic effect. And this one occurs when you have an optical wave and you combine this with a DC field, low frequency. It could be microwave, but it is much lower than you would expect in optics. You do the same thing, you find the square of this, you ignore the terms that we looked at earlier, the frequency doubling and the rectification, and you find that if you square this, you get a cross term between this term and each of these. And you get an extra factor 2 that you see here. Okay? Now, if you so this is your nonlinear polarization, then indeed, that doesn't seem to give you a new frequency. It still oscillates at omega. But if you now add this to the linear term, which was your epsilon naught chi times the incident field, you see that you add where you had chi before, you now get this extra term 4d e sub dc. Okay? The refractive index is again the square root of this, and so you find that one of the effects of this quadratic nonlinearity is that your refractive index becomes a function of an applied DC field. Okay, now that is neat because that means that you can essentially dial in your refractive index. Again, this is a pretty weak effect, but there are geometries that bring this out quite clearly. And this is the relation between the refractive index change and the applied field. And again, when you do this in practice, there are lots of tensor things that make life difficult, but or tedious, but don't change it. So one of the standard geometries where this is used is in this is called the electro-optic effect, I should say. And the electro-optic effect was in fact discovered before the laser, because you don't need a high intensity beam, you just need a large DC field. And so the theory for this is another mess which has nothing to do with the standard Bloomberg type treatment, but anyway, it doesn't really matter. So the geometry then is a Matjin interferometer. You have two arms, and here you put one of these you make this out of an electro-optic material with an applied voltage, and remember, when you apply the voltage, the refractive index here changes. And you can see that if the total nonlinear phase that you get here is pi, then the light from this arm will interfere destructively there. Okay? It was always a favorite question when I was in graduate school. What happens to the light when it interferes destructively there? Well, it kind of leaks away into the substrate, but it doesn't go into this waveguide. Okay, so if you now look at the transmission as a function of voltage, it is a sinusoidal function. When the phase difference is pi, then you get zero transmission, and then when you change it back again, you get high transmission. And so your transmission output power as a function of applied voltage has this sinusoidal behavior as I show here. And this is how most optical modulators work. Okay? So these are a couple of traces, applications of the electro-optic effect. This, so you come in with a DC light beam, and by applying this voltage, you get various information carrying signals out. This is an NRZ and this is an RZ signal. The details of which don't matter. This is here just to illustrate modulators. Okay, now there's a couple of other things that you can get out of these quadratically nonlinear media. Let's now come in with, oh, I forgot to change the J's here, I'm sorry. This should be minus I's. Let's come in with two fields, one at omega 1 and one at omega 2. And remember the polarization, the nonlinear polarization is proportional to the square of this. Now, there's a couple of standard terms. This is again your rectification. You get doubling of this term, doubling of omega 2, but then you get two new ones, and that's then the last two effects that you can expect to see with these quadratically nonlinear materials. You get some frequency mixing. You get something out which is the sum of omega 1 and omega 2, and you get the difference as well. And I'll talk a little bit about each of them. So some frequency mixing is, again, you get a frequency omega 1 and frequency omega 2. What comes out is the sum of them, of which the second harmonic generation is, of course, a degenerate example, because there your two input frequencies happen to be the same. Now, I also have a demo there, and this is a pretty rare laser pointer. This is a yellow one. So this yellow laser pointer, let me just go through the next page. So the yellow one comes out of, again, this neodymium Jaeger laser, but it blazes at two different frequencies. It has a 1064 line, which is the really strong one, but it has an outer line at 1342. It's another transition in the neodymium rare earth atom. And if you add those two frequencies, you take the inverse of that, add them up, take the inverse again to get a wavelength, you find that that corresponds to 593. And 593, as it happens, is in yellow. You may remember the sodium is 589, so this is just a little bit tad longer than the light coming out of a sodium lamp. And so let's see. Let me see. It's running out of batteries, I'm told. But this is yellow. Okay? So this is an example of some frequency generation, where you get two different infrared beams that somehow by magic, which I will tell you about towards the end of this lecture, you get a yellow light out. Now these yellow laser pointers are quite rare, but I managed to get one special for you. Isn't that great? All right. One of the other applications is to mix the YAG laser with a CO2 laser to get frequencies around 1.06. Okay? But the yellow laser is one of the more obvious applications. Then in general, you can have so in general you can have processes of this type. You get, this is the sum frequency mixing that I mentioned earlier. This is signal amplification, where you come in with a strong pump, a weak signal, and by this nonlinear process, you get an increased amount of omega-1, and you get some other frequencies generated as well. This is difference frequency mixing. We'll talk about that in a minute. This is a filter here that filters out the stuff you don't want. And then there are optical parametric oscillators where you put in a pump of omega-3, and by messing around with the mirrors and other things, you can get in principle, a continuously varying wavelength coming out. Basically, by splitting this omega-3 photon into one at omega-1 and at omega-2, so that energy is conserved. And again, by playing your cards right, you can tune these two frequencies. Now, one of the applications that has become important in this recently is what is called difference frequency mixing. You may know that there is a field that's been maybe 10, 15 years old. It's called terahertz science, or it's the science of terahertz radiation. So it has a wavelength in a terahertz regime. It's smaller than optics, but not hugely smaller. It's not as small as microwaves. It's a frequency regime that traditionally hasn't been particularly easy to deal with. There are not good sources in that regime, and they're not good detectors, or they used to be not good detectors. So traditionally this is hard. Now, one of the ways to generate light in these at these wavelengths is by frequency difference, difference frequency mixing. So you come in with a frequency omega-1, and that separates into a smaller photon with a smaller frequency omega-2, and to satisfy energy conservation, you need a third photon with a frequency that makes up the difference. Okay? And if omega-1 and 2 are close together, then this frequency here is small. And in principle, then you have a tunable source of this terahertz radiation. This is an example taken from the literature. This is an example where you beat, and this is beating, you beat two lasers together, both of which are around 1.55 microns. They're different lasers, they have slightly different wavelength, and if you play your cards right, you can get an output around hundreds of microns. In this particular case, it's 230 microns, and you can see that, I mean, it's nanowatts, it's not huge, but it's tunable. It's very hard to get tunable sources in this wavelength regime, and nonlinear optics is one way of doing it. Okay, so now we have to kind of take the bull by the horns, so to speak. And this becomes a little bit messy. I'll go through this a bit quicker. because it's somewhat tedious, but it's in the end it is important. So I've told you about all the effects that you can get out of this quadratically nonlinear medium. It's frequency doubling, which is a degenerate case of some frequency mixing. You get this difference frequency mixing that gives you the terahertz radiation. It's the optical rectification, this somewhat obscure effect that is not particularly well known and not particularly important. And that's about it. There's no more flavors. But there is this other problem that I mentioned earlier, and that problem is associated with the fact that it is very noble to have these dipoles oscillating at different frequencies inside your medium. But in order to observe it, that radiation needs to come out. And in order to do that, you require that the contributions from all the atoms in your medium do not interfere destructively with each other, because if they do, you don't see it. And so what we'll be doing in the next couple of slides is just see how you develop a theory for it. And in order to do that, you need to combine this effect that I talked about earlier, namely the generation of this nonlinear polarization. You have to combine that with what happens to these dipoles radiate, and what you want to see then is the sum of all those contributions, and therefore you have to trace how this newly generated light propagates through your optical. Okay? Now there's a couple of ways of dealing with that, one of which is coupled wave theory. It has been developed for all these nonlinear processes. They're all variations on the same theme. So I'll just use second harmonic generation as the canonical example, because for all the other cases, it is essentially the same. Some of the frequencies change, but apart from that, it is essentially the same. Okay, so remember how we did this. We start with the wave equation where this should be n squared, I'm sorry, rather than a 1. We have a source term here on the right-hand side, which is associated with your nonlinear polarization. The mental pictures, you have all these atoms there, work as little antennas. These antennas generate new frequencies, and you want to know the effect of that when you put a detector outside your medium. Okay, this is your input, and therefore your nonlinear polarization is this, and so your source term is this, where Q and R is the same, so this should be 2 omega. This is still a general theory, but I'll focus down to second harmonic generation very quickly. All right, so I have, and again, this should be n squared, I left it out. So I have now my wave equation here with a source term that falls off the page, but that looks like this. So I have all these different frequencies, okay? Difference, frequency doubling, some frequencies. Now, one of the things that we will see, and this is that getting these dipoles to interfere constructively with each other is difficult. You have to do something actively to do it. So unless you take precautions, it interferes destructively. Now that is the thing that saves you here. Because in principle you have all these different frequencies floating around in your system, and it becomes really tedious to keep track of all of them. But what saves you is that most of them interfere destructively unless you do something. And therefore you can concentrate on one of them. Of course you can only make this approximation once you know the answer. In this case we know the answer, alright? So again, unless you take precaution, nothing is going to happen. So we can ignore all of them except the one for which we're going to take precautions. And that's going to be the second harmonic symmetry. And if you then work this out, you'll find that you have a wave equation for the fundamental frequency and a wave equation for the second harmonic frequency. They have a different wave number, K1 and K2, and there is this source term on the right hand side. Okay? So here you can see that what the meaning of this is. There's a nonlinear coefficient here. The epsilon naught and mu naught are just social members. They don't do anything, they just eat and drink. So let's not worry about them. The D is the magnitude of your nonlinear coefficient. The omega here is a bit of a social member too. But then you have amplitudes of your field at omega 1, and you get the square. Okay? So that generates the second harmonic. Now, like all these processes, if you can go up in frequency, you can also go down. And so the frequency, the fundamental frequency does its own thing, but also has a source term on the right-hand side. And this is now a mixing term of at omega 2, which is 2 omega, mixes with omega, back to omega. Okay? So this is the up conversion, and this is the down conversion. The terms look very similar, except they're factors of 2 floating around, which you can work out when you're very careful, but apart from that are not particularly interesting. Okay? So these are the kind of problems we have to solve. Now, you can go a little bit further then. Doesn't worry too much about this. Okay. Then you make an approximation here, and the approximation is one of the standard ones you have in optics, and it has a number of different names, one of which is the slowly varying envelope approximation, or SVIA. And what that means is you say, well, these nonlinear effects are really pathetically weak. They really are. Right? Notwithstanding these laser pointers that burn your eyes out. These are pretty weak effects. Okay? And so, if you have this generation of this green light from the infrared photons, that's a pretty gradual process. It happens over many wavelengths of light. It doesn't occur in a very small region. It occurs over a region that's maybe a millimeter in length. Thousands of wavelengths. Right? So it grows gradually inside this medium. And for that reason, the amplitude, which is in the linear regime is constant, it varies here as a function of position. But you can say, well, since this second harmonic generation is pretty weak, it occurs over long length scales, much longer than the wavelength of light. And for that reason, if you take the derivative, if you look at this term here, you get a del squared, and you get basically the second derivative of this term here, right? And you get 3 terms out. You get a k squared, which cancels that one. You get this cross term, which is a first derivative here with a k, an ik coming down. And then the third one, the third term is a double prime on the a, d squared a dz. And you say, well, this envelope is so slowly varying that this second derivative is essentially negligible. And in that case, you can replace this by that, and it became your second order differential equation. It becomes a first order. And then you're basically done. You're off to the races. And if you do some normalizations, then your relevant equations turn into these 2. So this is the amplitude of the fundamental frequency, the amplitude of the second harmonic frequency. This is the remnant of what I said earlier. 2 fundamental frequency photons combine to give you a second harmonic one. A second harmonic one and a fundamental one combine to give you back a fundamental. There's some G, some kind of coupling coefficient that depends on many things, including the magnitude of the nonlinearity, a couple of other things. Let's not worry about that too much here. The business end is this position-dependent term. And this is the phase matching term, and it depends on K2 minus 2K1. Now, what on earth would that be? Let's just have a quick look what that would represent. Well, this delta K parameter, as I mentioned, is K2 minus 2K1. Let's just look at the definitions. K1 is omega N1 on C. K2 is the relevant frequency times N2 on C, where the relevant frequency, of course, is 2 omega. So you take these definitions of Ks, put them in here, and what comes out is that the condition for this to be 0 is that the refractive index at omega and at 2 omega are the same. Now you can ask the question, perhaps, that's pretty innocuous. What is the likelihood that the refractive index at frequency omega and a frequency twice as large are the same? Now, in fact, you have butlers. That's a nice Australian term, which means no way. And the reason is, of course, that optical materials, we're interested here in transparent materials, otherwise it all goes kaput. Now, this shows refractive index versus wavelength rather than frequency. But normal, ordinary optical materials have normal dispersion. And what that means is that the refractive index goes up with frequency or down with wavelength. That is essentially associated with the fact that you have big resonances in the infrared, you have big resonances in the ultraviolet, which have absorption associated with it, and the refractive index, as a consequence of that, must go up when the wavelength goes down. Okay, now, this is a strong effect, and especially when you have two frequencies that are an octave apart, that is really significant, and therefore the refractive index at omega 1 and omega 2 is in general not the same. They're in general different. All right? And as we will see, that then screws you up when you want to do this second harmonic generation. Let us for now, though, assume that we somehow by magic, and I'll tell you later how to do that, that you have managed to do that. Let's then solve these differential equations. Now, this is nonlinear optics, so the differential equations you get are nonlinear. Okay, that's the deal that makes it hard but also interesting. Boundary conditions. It turns out that the solutions to these couple nonlinear differential equations are sets and tangents. Hyperbolic set. So set is one cosh and hyperbolic tangent. And let me look at that. These are amplitudes. If you look at the intensities, which are indicated by phi, then you find that the second harmonic goes up as a hyperbolic function, the sech goes down as a hyperbolic secant, and they look like that. The sum is conserved. This is not the intensity, this is the number of photons. If you, these have twice as much oomph than these photons because the frequency is twice as high, so energy is conserved. Okay? So, when you have this perfect phase match, somehow by magic, you manage to get those frequencies the same. You get this very strong second harmonic out on the other side, and the fundamental frequency disappears. And that is what you get to some approximation in these green laser pointers, an example of which I showed you earlier. So this is the ideal situation. If you make a structure long enough, you can make your conversion efficiency arbitrarily high. And I'm starting to worry a little bit about time, so let me go quickly through this. This just shows you the parameter. If you have a finite length, then your efficiency depends on the nonlinear coefficients, the length, and the power. And it also depends on how tightly you squeeze your light together. Let's not go into it in detail. Let's now look at what happens if you don't satisfy this phase matching condition. Right? When you do phase match, you get this arbitrarily high efficiency. Let's now assume it's low. Now, it turns out that, again, this is something that you can only do once you know the answer. If you're not perfectly phase matched, your efficiency in general is pretty low. And therefore, you can make another approximation and say, well, if the efficiency is low, then the amount of power in my fundamental is going to budge, barely budge. I mean, if I come in with 1 watt, it may go down to 0.96 watts. But it's not going to do very much because it's poorly phase matched. So let's assume A1 is constant. Then I can trivially integrate this expression, and what I find is this. Right? This becomes an e to the minus delta KL minus 1, and that becomes a sine function as I pull out e to the minus I delta KL 2. Then this becomes 2I times the sine function. And that's the sine function you get here with half the work. Okay, so if I now look at the efficiency of this second harmonic as a function of this parameter delta K, then I get something like that. You get the maximum efficiency of delta K is 0. However, when delta K is non-zero, you see that you crash pretty quickly. Right? It's very close to 0. The functional form here is sine x on x. Okay? And not only do you see that it crashes pretty quickly, but it's kind of self-defeating, because one way of getting the efficiency up is to have very long structures. But you see that when you have very long structures, your condition here becomes tighter and tighter. So you're kind of screwed no matter what, to put All right? So, unless you're in very unusual circumstances, and some of my experimental colleagues are in those circumstances, some of the experiments they're doing at the moment, and one of my colleagues will talk about that. Unless you are in very special circumstances, you really need this delta K equal to 0. Otherwise, you can't really generate any of these yellow or green or whatever frequency conversion you want to do. Let me give you a little bit of intuition for what is happening. And this will also point to one of the ways to deal with this. This is this figure I had earlier. You have your sinusoidal driving field that, because of the nonlinear response of your atoms, gives you a nonlinear polarization. This is the linear component, and this is the nonlinear component, with twice the frequency. It also is roughly twice the spatial frequency. Okay? But the idea then is as follows. My second harmonic photons are generated at different positions inside the structure. And again, I want to play my cards such that at the end of the structure they're all in phase with each other. However, that is not happening. You can see then what happens, and in order to prove that I will need another 10 or 15 minutes, which I don't have, so let's not worry about it. But you can perhaps understand this without proof, that initially they're more or less in phase with each other, but then in this second bit, they are out of phase. And so if you look at the second harmonic amplitude inside the structure, it goes up, and then it goes down again. By the time that the ones here and the ones in the second bit interfere destructively with each other. So that at the end you have 0. And so your second harmonic amplitude inside the structure goes up and down and up and down, which is why you never get anything out on the other side. It just keeps oscillating back and forth, and oops, I'm mixing up my pointer with my. Oh, sorry. No. Which is what gives rise to a curve like this. Here it's all in phase. Here just cycles back and forth. All right, and you get these side winds because the period of this oscillation depends on delta K. And if you have exactly an integer number of these oscillations in your structure, you get 0. So that's where that comes from. Okay. So then we need some strategies to deal with this phase matching, right? As I've argued, you really must do phase matching, otherwise nothing comes out. And this, of course, justifies my assumption earlier to say I'll ignore all the nonlinear processes that occur. I'll only deal with the one for which I'm going to make an effort, because the other are 0. Now, the traditional approach here is using a birefringent medium. So there's a noun missing that should be birefringent phase matching. And the idea there is the following. It makes use of the properties of birefringent media. And I have thought about it, I would have taken one with me, because we have a nice piece of such material in school, but I forgot. So these are materials which have a preferred direction. They're crystals. Okay, glass doesn't have it, but some of those crystals, particularly those crystals that I mentioned earlier. And they have the property that if you come in with, if the light is in this medium in a particular direction, then that light has 2 different refractive indices, depending on the polarization. So if it's up, say, it has 1 refractive index, and if it is horizontal, it has another refractive. That's just a general property of birefringent materials. Okay? Now, so we have then 2 mechanisms by which refractive indices differ. We have a dispersion, namely the fact that an omega and 2 omega have different refractive indices. And we have the fact that this polarization and that polarization have different refractive indices. Okay? And so the trick that you can now see coming is that you try to cancel those out. One of the frequencies has, say, this polarization, the other frequencies has that polarization, and then again, the refractive index difference that you get from this this and that polarization cancels exactly the refractive index difference you have between this frequency, omega, and that frequency, 2 omega. All right? It's very fiddly, but it can be done. The properties of these crystals are well known. It's one of these things that's messy, it's not pretty, but it works. Okay? And so, for obvious reasons, that's called birefringent phase matching. Okay, now, in order to do that, you need a birefringent material. And so some of these materials I showed you earlier, the ADP, the KTP, the lithium niobate, they all are birefringent materials, so you can play this trick. Okay? Regrettably, gallium arsenide, which had this whoppingly large nonlinear coefficient, you remember that most of these materials had this in units of picometers per volt. It was a few, and on a good day it was 15. Right? Gallium arsenide is 300, right? Massive. But you can't phase match it because we're not using this method. Because it is an isotropic material. It has only one refractive index rather than two for a given propagation direction. So this works, and people until 20 years ago, everybody did their second harmonic generation in this way. It was a standard thing. Most of these crystals came out of China because the Chinese are very good at growing crystals. And you just buy them off the shelf, and you have to come in at a particular incident angle because otherwise they won't work. Because those two refractive indices depend on the incident angle. All right. The other method is now the preferred one, though it has some disadvantages, and it's called quasi-phase matching. And though the idea has been around for donkey's years, which is another Australian expression, which means many, so for many years, technically it's very difficult. It has been developed only in the last 10 or 15 years. And the idea is then the following. This is that figure I showed you earlier of this second harmonic being generated here, and the bits in this second half cancelling the bits in the first half. That's the problem. Now, suppose you had a knob by which you could switch off the nonlinearity for in particular positions in your structure. Suppose you turn it off in this red region here, right? Then intensity would go up, and then you suddenly switch your nonlinearity off so it remains constant. And then in this next bit here, you switch it on again, so it keeps going up. Because in the region where it goes down, you switch your nonlinearity. Right? That is the basis of quasi-phase matching. And what you do in practice is not so much switching it off, but this nonlinear polarization, this type 2, has a direction. And what you can do is even better than this. Rather than switching it off, you can flip its sign periodically. That's called periodic polling. It was a process developed originally in the former Soviet Union, was taken up by people at Stanford who did a lot of work at it and really developed this so that it is a mature technology now. And the phase matching in these laser pointers is all quasi-phase matching. Right? So, what quasi-phase matching is that you have this material. It was first developed in lithium niobate, some other materials as well. The sign of the nonlinearity changes, flips periodically, and therefore for a certain wavelength, a range of wavelengths, you get your quasi-phase matching, because the regions where you otherwise interfere destructively, it now interferes constructively because you flip the sign of the nonlinearity. You've thrown in effect, an extra phase of pi. Now, this was all pretty sketchy because I was fearing that I was getting towards the end of my lectures, as indeed I am. Just a couple of pros and cons. This is the traditional method. This is the quasi-phase matching. This is as efficient as it gets. Here, you're always down by a factor of 4 on pi squared, which I'm happy to explain to you now. So this is about 40%. This per unit length and per unit intensity, this is 40% as efficient as that. However, there are some considerable advantages. Birefringent phase matching basically relies on crystals in nature. There's nothing much to engineer there. You can twiddle with the angles, but that's more or less it. You ultimately rely on crystals that are that you have to grow. These, because you can mess around with the period and all kinds of other properties, can be engineered. So in a sense, they're much more interesting. And then also something that I won't have time to go into in detail. These have a narrow bandwidth. These quasi-phase matching materials have much broader bandwidth. Again, I don't have time to go into it. And for that reason, even though you're down by 4 pi squared, things like this make it that just about every practical application of this second harmonic generation or some frequency mix all make use of these quasi-phase matched materials. And I think that is more or less it. Yes, so this is my last slide. You're invited to join locals. So the School of Physics is this kind of yellowish building that is in that direction. On the roof, on the right-hand side, seen from here, there's a barbecue where you can talk to some of the locals and eat some of the locals as well. I'm told there is kangaroo meat available, so it's quite nice. So don't think too much when you eat it, but so anyway, so you enter. Oh, I don't know where you enter. There's a couple of doors. I don't know why the entry is here, but the doors presumably open. This is where you want to go. All right, and I'm told there's lots of beer as well. So if you don't like get into beer, drink the beer. Okay, thanks guys. That's it. All right. Any questions, or you want to get to?